All right. So there is a point that we have gone through it, but there's a point that I would like to emphasize here, which is a common misconception that one has about a PN junction regarding the reverse saturation current. Okay. We have discussed in the notes, but let me emphasize it once more here. We have a diode. This is the equation that we recognize about a diode, right? ID equal to IS exponent V by NVT minus 1. And the common term for this is the reverse saturation current, right? And which makes sense if I look at this expression here, that if I apply a voltage which is negative, say a negative reverse bias minus VR, we substitute minus VR here, and if VR is large, then this term becomes 0, and we get ID minus VR is equal to minus IS, right? And therefore, and since this is independent of VR, whether I apply 1 volt, 2 volt, 3 volt, 4 volt, it doesn't really make a difference here. ID remains IS. So we say reverse current has saturated. Saturated means it's no longer changing with bias. And therefore, the term that we have for IS is, this is the reverse saturation current. And that's a misconception. Why is it a misconception? Well, let's look at this example, right? This example we've been considering, our PN junction here, symmetrical PN junction, 5 times 16 here, 5 times 16 here, dP is the diffusion constant here, dN is diffusion constant, tau and tau p, all these are given here. This is the IV characteristics I'm showing you right now obtained from simulation here. This is the IV characteristics. Correct? Can we recognize 3 regions? This is the place where my diode behaves like an ideal sort of diode here. This is where resistances become important, and this is where recombination occurs. So if I look at this particular region here, right, and I can fit it with an expression, diode equation here, J equal to 3.1 10 power minus 11 exponent QB by 1.02K. Ideality factor is close to 1. And according to this, what is my saturation current? GS is 3.1 into 10 power minus 11. So what do I expect? That if I reverse bias, according to my previous statement, if I reverse bias my diode, I should get this much current. But when I actually do simulation and calculate what is the reverse bias current at minus 5 volt, what do I get? 4.1 into 10 power minus 7. Right? Very different from this particular value. So my actual reverse current is not GS. It's actually much different from this particular value here. This is 3.1 into 10 power minus 11, and this is only 4.1 into 10 power minus 7. And what are the reasons? The reasons are if you go back, that this current, this expression that we derive, right, J equal to Js exponent QV by KT minus 1. This, yes, we are neglecting recombination current here, but this expression is actually true for forward bias. It's true for forward bias only. It's not true for, even if I were to take recombination within the depletion region here, that would add a term, but the term still will not correctly predict the reverse leakage current. Still would not predict the reverse leakage current here. And so what happens is we just saw the actual reverse leakage current has 2 components. This is the first component and this is the second component, right? And this first component is what we just saw, is what enters into GS. GS is this first term here. And we know that reverse leakage has two components, generation outside the depletion region here and generation within the depletion region. And we saw that the first term is considerably smaller than the second term, right? This is 3.1 into 10 power minus 11 and this is 4.1 into 10 power minus 7. Right? So taking the forward characteristics, calculating GS from there, and then hoping that GS will correctly predict my reverse leakage current, this will not work, right? Because it's ignoring this particular part here. Now, if you were to say that, suppose I included the second term as well, right? The second term as well, even then it will not predict correctly. Let me show you now with the actual diode here. So, for example, we had taken this 1N4007 diode, right? And this is the measured ID VD characteristics here. And in this case, in this particular diode, we don't see a region where ideality factor is close to 1. We don't see that here. For example, if I were to look at this region here, which shows an ideality factor, it shows an ideality factor of around 1.5, and shows a saturation current of 5.9 into 10 power minus 10. Now, why is the ideality factor 1.5? What is the reason? Why is it not 1? Why is the ideal diode equation not valid? Well, go back and see, as we said, this is the, it represents the ideal diode equation, right? And this has an ideality factor of 1, n equal to 1. But then, as we discussed, that in addition to this particular term, there's recombination within the depletion region also. So I should add another term here. And that other term is what? 2 kT here. So the actual current has two components. One is ideality factor n equal to 1, the other is n equal to 2. And therefore, the two of them together then result in, when both the components are significant, they cause an ideality factor somewhere in between 1 and 2. So that's what we see in this particular PN junction. Actual 1 and 4007. When I see an ideality factor of 1.5, it means that both my 1 kT component and 2 kT components both are significant, right? And we get IS equal to 5.9 into 10 power minus 10. If I fit it here, it's an exponential, and we get a saturation current of so much, right? So now, if I go with the simplistic view, this is the equation which is valid. If I put V equal to minus VR, I would expect a reverse current of 5.9 into 10 power minus 10, right? This is what I would expect. Well, we did measure the reverse current, and what did we get? So I'm going to expect a reverse current of 5.9 into 10 power minus 10. And what did we get here? Look at the experimental measurement. This is reverse bias. Because the current is low, it got a little bit of noise here in the current here. What is the current? 4 into 10 power minus 9. And so this is one order of magnitude higher than this particular current here, 5.9 into 10 power minus 10. Right? So your reverse current is not going to be your reverse saturation current. Right? It's not going to be reverse saturation current. In silicon PN junctions and other PN junctions as well, you will find reverse leakage current is significantly different. In which case, you might expect the two of them to be the same. A small band gap material, maybe they'll come closer together. Okay, so that's a misconception that IS is the reverse saturation current. Well, ID at a reverse bias will not be equal to IS. It's not going to be that. Okay.